Hello, everyone. I'm Lucas. I'm a PhD student at University of Campinas, Brazil, and I'll be the speaker for our work named Connoisseur, Provenance Analysis in Paintings. I'll start with our motivation. We are interested in ways to analyze art. The reasons for that is that we understand art pieces as detainers of history that can tell stories to people that interact with it. In this vein, connoisseurship is an important ability held by the connoisseurs, individuals concerned with the study of art, with respect to its authorship, provenance, and all adjacent aspects. Current digital art repositories are constantly growing, indicating a rising interest in this domain by experts and enthusiasts alike. With that comes a proportional increase in importance of tasks such as art organization and categorization, provenance analysis, authorship attribution and matching, and finally, forgery detection. Machine learning can help us with all of these tasks and be used to create tools that assist individuals with their related interests. In fact, this is not exactly a new thing. Paintings are often analyzed with the assistance of classic machine learning and statistical models. Image decomposition and dimensionality reductions are examples of this, as well as feature extracting filters that can be used to represent characteristic brushstroke patterns in a low-dimensional feature space. And of course, data-driven strategies have gained a lot of traction in the last few years. For example, research applied to authorship, style, and media attribution are not uncommon. It is also noticeable a latent interest in generative adversarial models, which can be used to produce artificial paintings, as well as multi-objective optimization, which can combine the multiple aspects of information available to spawn better representation spaces. Here we state our research objectives. The first one is to design an effective data-driven strategy to learn discriminative features from the large painting collection. The second one is to investigate new ways of leveraging the multiple facets of annotated information available. In order to do so, we utilize the existing experimental setup provided by the Painter by Numbers challenge proposed in the Kaggle platform. This challenge can be summarized by the following question. Given a pair of paintings, were they created by the same person? The training set of this challenge comprises more than 79,000 paintings, each of which is associated with one of the 1,584 painters, 135 styles, and 42 genres. The test dataset comprises almost 24,000 paintings and more than 21 million comparison pairs. Furthermore, we observed the occurrence of unknown painters that do not appear in the training set. Evaluation is performed with the area under the receiver operating characteristic curve, or AUC. So our proposed strategy can be outlined as follows. We randomly sample 15 patches from each one of the images representing paintings. These patches are encoded with a convolutional network into feature vectors, which can then be embedded into a metric space where these patches can be compared according to some high-level characteristic. Finally, we fuse the patch level predictions into a painting level ones, obtaining our answer for the pair. We tested a few combinations of encoding and embedding networks. We'll detail three architectures which we think are interesting. The first one is also the simplest. We used painter information to partially fine-tune an Inception V3 network attached to a softmax classifier. The output signal is used as feature vectors to train a Siamese authorship discriminating head. And the second one, a conventional multitask setup is employed to learn painter, style, and genre information at once. Siamese discriminating head is attached to each one of the outputs, and each one learns to match authorship, style, and genre separately. A final binary classifier is then used to solve the PBN challenge. And the last one, we increased the number of units in the classification layer. It trained it as a multi-label classification problem, where the prediction variables are the concatenated painter style and genre information. We hypothesize that this model can create an authorship representation space that leverages the correlational information between the different label groups without suffering from the fast saturation caused by the softmax activation function. So here are our results. We report the area under the curve for the PBN test set, as well as for the unknown authors that do not appear in the training set. We compare the proposed strategy with the competition's winner, as well as a simple Siamese network trained with contrastive loss over the Euclidean distance. Firstly, using the Siamese authorship discriminating head provides significant improvement over the contrastive loss setup. As expected, we also observe an increase in score with the multitask setup. And finally, we're able to achieve the highest score among all of the architectures with the multi-label setup. And while none of these surpass the competition's winner in the test set, the multi-label and multitask setups show a significantly higher score over the subset of unknown authors that only appeared in the test set, indicating that these approaches can learn representations that better generalize for unknown classes. These are the saliency maps generated with the gradient backpropagation method over the multi-label model. At least in these samples, we observe a focus on highly detailed regions with extensive brushstroke work and strong color contrast. If we rank all of the genres according to their average AUC, we can see that the paintings from the genres tessellation, veduta, and bird and flower painting are more confidently matched by the model. Conversely, the model seems less confident when predicting religious paintings, self-portraits, and vanitas. So our conclusions: in this paper, we approached the authorship matching problem by combining individual scores from multiple observations of a single painting, each of which focusing on local regions that better capture brushstroke patterns instead of general image content. We combined multiple aspects of the available information and obtained a competitive score within the PBN challenge, and found out that modeling these tasks as multi-label problem results in better generalization towards unknown classes. For future work, we intend to approach the class unbalance problem using artificial synthesis of art. We also expect to study better pet selection strategies using, for example, attention methods. And lastly, we believe to be paramount to study this problem in a more realistic setting. For example, by accounting for the possibility of co-authorship or contemporary and obscure domains where very few samples are attributed to an author. And finally, to extend and validate this work against forgeries. These are my references, and I thank you all for your attention.